So if I try to switch the lth and mth particles, then what I'm going to do is I'm going to take the coefficient and effectively change the coefficients to swap those two indices. So if we're not allowed to change the results of any possible physical experiment when we do this switch, can these coefficients be different at all? And the answer is only just. If there's any different phase relationship between coefficients for different states, then we can measure that. There's some observable that will measure that. So there's some experiment that will tell. So the only kind of state that has exactly the same results for all experiments is one that has all possible pairs of combinations of basis states have the same relative phase. And that means that these two coefficients must be the same up to a global phase. Now supposing we were to take two particles and swap them, and then swap them back, we have to have not just the same results for all experiments, but that's exactly the same wave function. So doing this process twice must give us the actual same coefficients exactly, which means that this phase factor squared has to be 1. Therefore, there are only two possibilities. Either swapping two particles gives you exactly the same coefficients, or swapping two particles gives you a minus sign. Particles that have this symmetric property are called bosons, and particles that have this antisymmetric property are called fermions. And everything in the universe is either a boson or a fermion. Now with luck you've heard these terms before. For example, in high school chemistry you were probably told that two electrons can't be in exactly the same state as each other because of the Pauli blocking principle. Now the reason for that is that electrons are fermions. If we have a look at just say two electrons, let's look at the coefficients for this many-body wave function for where both of these two electrons are in the same single particle state. In other words, we're going to look at the coefficients where we've got a repeated index. If we look at the property of fermions, which is that the coefficients must be antisymmetric when we swap the two indices, then we realize that there's really only one number that is minus itself, and that is 0. So the coefficient of any state that has two electrons in exactly the same single particle state is 0. In other words, there's 0 amplitude there. That can't happen. So fermions can never be in the same state as each other. Now this doesn't apply for bosons, of course, because you don't have that minus sign there. Without that minus sign, our argument that this equals 0 falls apart, and indeed bosons can be in the same state. In fact, you might have heard that bosons like being in the same state. But in order to understand that, we have to look at some dynamics. One final comment I'd like to make is that the symmetry or antisymmetry of the coefficients of the states for indistinguishable particles actually seriously reduces, in both cases, the dimension of the resulting Hilbert space. So for distinguishable particles, you've got the full tensor product, whereas for indistinguishable particles, a lot of those coefficients depend on each other, and so they're redundant. And so the size of the actual Hilbert space is much smaller. It's quite a small subset of the full tensor product Hilbert space. It's still very large as the number of particles goes up, but we can see that we really should be trying to develop a notation and a system whereby we can describe the independent states without using an overcomplete basis.